The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so today's lecture is going to be on finite-state Markov chains, and we're going to use the matrix approach. So in last lecture, we saw that the Markov chain we could represent it as a directed graph or as a matrix. So the outline is like we will look at this transition matrix and its powers, okay? And then we want to know whether this P of n is going to converge for a very, very large n, okay? Then we will extend this to our ergodic Markov chains, ergodic unit chains, and other finite state Markov chains. So remember in the Markovity, these Markov chains, the effect of the past, okay, on the future is totally summarized by its state. So we want to analyze the probabilistic properties of the sequence of these states. So whatever this state you are in, all the past is totally summarized in that state, and that's the only thing that affects the future. So an ergodic Markov chain is a Markov chain that has a single recurrent class. Okay, and it's aperiodic. So this chain doesn't contain any transient states, and it doesn't contain any periodicity. So ergodic unit chain, okay, is just ergodic Markov chain, but it has some transient states in it. Okay. So the state x of n of this Markov chain at step n depends only on the past to the previous step. So for n steps, we want to be in state j. And then we have this path, x of n minus 1 is I, and so forth up to x naught. It's just the probability from I to j, from state I to state j. So this means that we can write the joint probability of all these states that we're in. So x naught, x1, all the way up to xn, okay, as a function of these transition probabilities. So in this transition probability matrix, okay, we can represent these transition probabilities. We see that here, we have in this example, this is a 6-state Markov chain. So if I want to go from, say state 2 to state 1 in one step, it would just be P of 2, 1. Okay, if I want to go from state 6 to itself, it's this last one, which is P of 6, 6. So this is a probability transition matrix. So if we condition on the state at time 0, okay, and then we define this P of ijn is equal to the probability that we're in state j at the nth step, given that we start x naught is equal to I. Let's look at what happens when n is equal to 2. So in a two-step transition, we go from I to j. It's just the probability that at step 2, x2 is equal to j, x1 is equal to some k, okay, and x naught is equal to I. So remember, we started in state I. So, but this has to be multiplied by probability that x1 is equal to k, given that x naught is equal to I. And we have to sum this over all the states k in order to get the total probability from oh, stand back? OK. Great. OK. So this is just a probability of ij in 2 steps. It's just a probability of I going to k, OK, times the probability k going to j, OK, summed over all k states. So we'll notice that this term right here, the sum over k of ik, kj, is just the ij term of the product of the transition matrix P with itself. So we represent this as P squared. So we multiply the transition matrix by itself. This gives us the two-step transition matrix of this Markov chain. So you just look at the I. If you want to go from I to j, you just look at the ij element, okay, in this matrix, and that gives you the probability in 2 steps going from state I to state j. So, okay. So for n, we just iterate on this for successfully larger n. So for n state, to get from state I to state j, okay, we just have this probability x of n given j, given x of n minus the previous step is equal to k, x of n minus 1 equals to k, given x naught is equal to I, summing over all k. So this means that we broke this up for the n step. In the n minus 1 step, we visited state k, and then we multiplied that 1-step transition from k to j, because we want to arrive at j starting at I. Okay, but again, we have to sum over all the k's in order to get the probability from I to j in n steps. So P of n right here, this representation is just the transition matrix multiplied by itself like n times. And this gives you the n-step transition probabilities on this Markov chain. So computationally, what you do is you take p squared, p to the 4, if you want p to the p to the 9th, you just take p8 multiplied by p to multiply by this. So this gives us this thing called the Chapman-Kolmogorov equations, which means that when we want to go from step I to step j, we can go to an intermediate state and then sum up all the states that would go into the intermediate state. So in this case, if the step is m plus n transition, we can break it up into m and n. Okay, so it's the probability that goes from I to k in exactly m steps and k to j in n steps, summing over all the k that it visits. Okay. On its way from I to j. So this is very useful quantity that we can manipulate our transition probabilities when we get to higher orders of n. All right. So the convergence of p to n. So a very important question we like to ask is, as n goes to infinity, okay, whether this goes to a limit or not. In other words, okay, does the initial state matter? Okay, all the initial states matter. In this Markov chain. So the Markov chain is going to go on for a long time, okay? And at the nth state, where n is very large, okay, is it going to depend on I, or is it going to depend on n, which is the number of steps, okay? If it goes to this quantity, some limit, then it won't depend on this. So let's assume that this limit exists, okay? If this limit does exist, okay, we can take the sum of this limit, okay, and then multiply by p of jk, and summing over all j. So we do sum over j. So we're going from j to k on both sides, and we sum over all j. So if we take this limit right here, we notice that, okay, this left side, going from I to k to n plus 1, is just that this limit at state k exists. Because we assume that up here, this exists for all I and all j. So therefore, if we take the n plus 1 step, we take this m going to infinity of I to k, it has to go to pi of k. Okay. So when we do this, we can simplify this equation up here. And if this limit exists, we have this pi sub k for all the states in the Markov chain. So this is just a vector. So pi sub k is equal to pi sub j times probability from k to j, sum over all j. So if you have an m-state Markov chain, you have exactly m of these equations. And this one, we'll call it the vector pi, which consists of each element, this equation. Okay, this is if the limit is going to exist, but we don't know whether it does or not at this point in time. Okay, so if it does exist, what's going to happen? So that means I'm going to multiply this probability matrix p times p all the way. And if the limit exists, okay, then that means for each row, they must be all identical. Right? Because if we say the limit exists, then going from 1 to j, 2 to j, 3 to j, 4 to j, they should be all exactly the same. This is also equivalent to saying when I look at this large limit, okay, as n is very, very large, okay, if the limit exists, that all the columns, all the elements in the column should be exactly the same as well, okay? Or all the rows. So the elements are equal to each other, or all the rows. If I look at the row, which is going to be this pi vector, it's going to be they should be the same. Okay, so we define this vector. Okay, if this limit exists, the probability vector is this vector pi. Okay, pi 1, because we said it was an m-state Markov chain. And if each pi sub I is non-negative, and they also obviously have to sum up to 1. So this is what we call a probability vector, and called the steady state vector for this transition matrix P. Okay, if it exists. So what happens is like this limit is easy to study, and in the future in the course we will study these pi equal pi p, this limited state steady state vector. Okay, for various Markov chains, and see, and it's quite interesting. Many things that could come about it. Okay, all right. So we noticed that this solution, it can contain more than one. Okay, it may not be unique. So if it contains more than one, it's very possible that it has more than one solution, more than one probability vector solution. But just because a solution exists to that, it doesn't mean that this limit exists. All right. So we have to prove that limit exists first. All right. Okay. So for a Markov chain, okay, here we have another way to express this, that these this matrix converges is that the matrix of the rows, the columns are all the elements in the column are all the same for each I. Okay, so we have this theorem, and in today's lecture is going to be completely this theorem. This theorem says that if you have an ergodic finite-state Markov chain, so when we say ergodic, remember, it means that there's only one class. Okay, every single state in this is recurrent. You have no transient states, and you have no periodicity. So it's an aperiodic chain. Okay, and then for each j, if you take the maximum path from I to j in n steps, this is non-increasing in n. Okay, so in other words, this right here, this is a non-increasing. So if I take the maximum path, okay, from state I to ij, give you exactly n steps. Okay, so that means this is maximized over all initial state I. So it doesn't matter what state you start. And I take the maximum path, and if I increase n, and I take the maximum of that again, the maximum path, this is not increasing. And the minimum is non-decreasing in n. So as we take n, the path from I to j, this n getting larger and larger, we have that the maximum of this path, which is the most probable path, okay, is non-increasing. And then the minimum of this path, okay, the least likely path is going to be non-decreasing. So we're wondering whether this limit is going to converge or not. And this theorem said that for an ergodic finite-state Markov chain, this limit actually does converge. So in other words, the lim sup is equal to lim inf of this, okay, and it will equal to pi sub j, which is the steady-state distribution. And not only that, this convergence is going to be exponential in n. Okay, so this is a theorem that we will prove today. Okay, so the key to this theorem is this pair of statements. Okay, that the most probable path from I to j given n steps. So this is the most probable path, is non-increasing in n, and the minimum is non-decreasing in n. So the proof is almost trivial, but let's see what happens in this. Okay, so we have a probability transition matrix. Okay, so this is a statement right here, and the transition is just one here and one here with probability 1, 1. Okay, in this case, if we want to say, okay, what is the maximum path that we're in state 2, okay, given n steps. Okay, so this we know that this probability alternates between 1 and 2. It's not increasing, it's not decreasing, it's always the same. Okay, so this bound is met with equality. Those two bounds are met with equality. Okay, so this here. So the second example is this. We have a two-state chain again, but this time from 1 to 2 we have the transition of 3/4. Okay, so that means that we have a chain here of 1/4. See, the minute we put a self-loop in here, it completely destroys the periodicity. Okay, any Markov chain, you put a self-loop in it, and the periodicity is destroyed. So here we have 3/4. So this has to come back with 1/4. All right. So in this one, let's look at the n step going from 1 to 2. So basically, we want to end up in state 2. Okay, and in exactly n steps. Okay, so when n is equal to 1, okay, so what is the maximum? The maximum is if you started in this state and then you went to state 2. The other alternative is you start in state 2 and you stay in state 2, because we want to end up state 2 in exactly one step. Okay, so the maximum is going to be 3/4 and the minimum is going to be 1/4. Okay, suppose you get n is equal to 2. Now we want to end up in state 2 in 2 steps. So what is going to be the maximum? Okay, the maximum is going to be if you visit state 1 in the back. So n is equal to 1. Okay, then p1 from 1 to 2 is equal to 3/4. Okay, so the probability from 1 to 2 in 2 steps, okay, is equal to 3/8. Okay. Okay, so it goes 1/4 plus 3/4, 3/4 plus 1/4. It should be with 3/8, right? Is that right? Yeah. Okay. Okay. So and then when p1, 2 to 3, if there's 3 transitions from 1 to 2, then it's equal to 9/16. So if for 2, if I want the transition from 2 to 2 in n steps, so p2, okay, is equal to 1/4. So it just stay by itself. Okay. So p2 in 2 steps. Okay, I can you don't have a choice. You have to go from 3/4 to 3/4, okay? So therefore, okay. And then, so that's 9/16. But the thing is, I can also stay here by 1/4 times 1/4. Okay, so that gives me 5/8. Okay, and so forth. Okay, and so forth. Okay, so so basically the sequence, okay, going from 1 to 2 is going to be oscillating, okay, between let's say 3/4, 3/8, 9/16, and so forth. And then the going from 2 to 2, it's going to be oscillating too. Okay, we can see that's 1/4, 5/8, 7/16. So what happens is this oscillation is going to converge, is going to approach actually 1/2. So if we take the maximum of these two, so P12 and P22, okay, so because that means that we're going to end at state 2, okay, and maximum over n steps, then we just look at these two numbers, the 3/4 and 1/4. If you want a maximum, then it's going to be 3/4. The 3/8 and 5/8, the maximum is going to be 5/8. The 9/16 and 7/16, the 9/16 will be the maximum. Okay. Then similarly, we compare it and we take the minimum, and the minimum is 1/4, 3/8, and 16. So we see that the maximum is going to be, it starts high, okay, and then it's going to decrease toward 1/2. And the minimum, what happens is it's going to start low, and then it's going to increase to 1/2. So this is exactly this one here. So P is a transition matrix in arbitrary finite-state Markov chain. Then for each j, this maximum path, okay, the most probable path from I to j n steps is non-increasing in n, and the minimum is non-decreasing in n. So you take n plus 1 steps from I to j. Okay, so we're going to use that Chapman-Kolmogorov equation. So we take the first step to some state k, okay, and then we go from k to j in n steps. All right, but then we sum this over all k. But this pk n, for state k to kj n steps, I can just take the maximum path. So I take the maximum, most probable path, okay, the state that gives me the most probable path, and I substitute this in. When I substitute this in, obviously, every one of these guys is going to be less than or equal to this. Okay, therefore, this outside term is going to be less than or equal. So now this is just going to be a constant. So I sum over all k, and then this term remains. Okay, so therefore, what we know is like if I want to end up in state j, okay, and it's for n steps, if I increase the step more to n plus 1, we know that this probability, okay, is going to stay the same or decrease. It's not going to increase. So you could do exactly the same thing for the minimum. Okay. So if this is going to be true, then of course, if I take the maximum of this, is also going to be less than that, because this is true for this lemma is true for any Markov chain. It doesn't matter. It just has to be in a finite state Markov chain. So this is true for any finite state Markov chain. So if I take the maximum of this is less than or equal to the maximum of the n step. So n plus 1, okay, steps. The path is going to be less probable when I take the maximum path, that the fact that I end up in state j than n. So, okay. So before we complete the proof of this theorem, okay, let's look at this case where p is greater than 0. So when we say p is greater than 0, this means that every entry in this matrix is greater than 0, okay, for all ij, which means that this graph is fully connected. So that means you could get from I to j in one step with non-zero probability. Okay. So if p is greater than 0, okay, let this be the transition matrix. So we prove this first, and then we'll extend it to the arbitrary finite Markov chain. So let alpha here is equal to the minimum. So it's going to be the minimum element in this transition matrix. That means it's going to be the minimum transition, the state that contains the minimum transition. Okay. So let's call alpha. It's the minimum probability. Excuse me. Okay. So let all these states I and j, and for n greater than or equal to 1, we have these three expressions. Okay. So this first expression, okay, it says this, that if I have like a n plus 1 walk from I to j, so I take the most probable of this walk, okay, over I. So my choice is like I can choose my initial starting state. In n plus 1 steps, I want to end up in state j. So I pick the most probable path. If I minus this, which is the least probable path, okay, but you get to minimizes over I, over the initial starting state. So this is less than or equal to the n step, okay? So exactly this, this term here, the n step, okay, times 1 minus 2 alpha. So alpha is this minimum transition probability in this probability transition matrix. Okay, so this one, it's not so obvious right now, but we were going to prove that in the next slide. So once we have this, okay, we can iterate on n to get the second term. Okay, so for this term inside here, the most probable path to state j in n steps minus the least probable path to state j in n steps, okay, is equal to exactly the same thing in n minus 1 steps times 1 minus 2 alpha. So you just keep on iterating this over n, okay, and then we should get this. So to prove this to this, we prove it by induction. We just have to prove the initial step, okay, that the maximum single transition from L to J minus the minimum single transition from L to J is equal to less or equal to 1 minus 2 alpha. So this one is proved by induction. Okay. So as n goes to infinity, notice that this term is going to go to 0. Okay, because alpha is going to be less than 1/2. Because if it's not, then it cannot. We can choose 1 minus alpha to be this minimum. Okay, so if this is going to 0, this tells us the difference between the most probable path minus the least probable path. The fact that we end up in state J. So if we take the limit as n goes to infinity of both of these, they should equal. Because the difference of this, we notice that it's going down exponentially in n. Okay, so this shows us that this limit indeed does exist and is equal. We want to prove this first statement over here, this first statement. So in order to prove the first statement, what we're going to do is we're going to take this ij transition, n plus 1 transitions, okay, and then we're going to express it as a function of n transitions. All right. So the idea is this. We're going to use the Chapman-Kolmogorov equations, okay, to have an intermediary step. So in order to this I to j and n plus 1 steps, the most probable path, we're going to go to this intermediate step, and then on to the final step. So what we're going to do is in this intermediate step is going to be a function of n. So we're going to take one step and then n more steps. So what we're going to do is, the intuition is we're going to remove the least probable path. Okay, so we remove that from the sum. Okay, in the Chapman-Kolmogorov equation, and then we have the sum of everything else except for that path, and then the sum of everything else we're going to bound it. Okay, once we bound it, then we have this expression ij. Okay, probability of I to j in n plus 1 steps is going to be a function of a max and a min over n steps with a bunch of terms. Okay, so that's the intuition how we're going to do it. Okay, so probability of ij going from state I to state j in exactly n plus 1 steps is equal to this. So it's the probability of going from I to k. Okay, this intermediate step. We're going to take one step to a state k, and then we're going to go from k to j in n steps, summing over all k. So this is exactly equal to this, from Chapman-Kolmogorov. Okay, so now what happens is like we're going to take, okay, so let's define that, before we get to this next step, let's define this L-min to be the state that minimizes P of ij n over I. So L-min is going to be the state that's going to be such that the choices I pick over I, that in n steps I arrive at j, that's going to be the least probable. Okay? So this is going to be, this is L-min over here. It's the L-min that satisfies this. Then I'm going to remove this. So this is one state. L-min is just one state that I is going to go to in this first step. Okay, so we're going to remove it from the sum. Okay, so then this is just here. Okay, so that path goes from I to L-min, okay, times min over L to j in n steps. So remove that one path from here. Now we have the sum over the rest of the case, right? Because we just removed that. So we have ik, kj to the n, where k is not equal to that L-min. So we remove that path, the one that goes to that state. Okay, so but P of kjn, so going from the path that goes from k to j in n steps, we could just bound this term by the maximum over L from L to J of n. Okay, so then we're going to take the most probable path in n steps such that we end up in state J in n. So this term right here is bounded by this term. Because it's bounded by this, that's why we have this less than or equal sign. Okay, so we just do two things from this step, to the first step to the second step. So we took out that the path that's going to minimize that would arrive at the jth node in n steps, and then we bounded the rest of this sum by this. Okay, so when we sum this all up, this is just a constant here. Okay, and ik here is just all the states that I is going to visit except for this one state L min. Since it's just all of them except for that, it's just 1 minus the probability that it goes from state I to L min. Okay, so this sum here is just equal to this sum here. Okay, so this arrives here. Okay, and this term is still here. Okay, all right. So going from here to here, what happens is we just rearrange this, rearrange the terms. Okay, so nothing happens from here. It's just rearranging. Okay. Now we have this term here. Okay. So we look at this term, p from I going to L min. Remember, we chose alpha to be the minimum single transition probability. Okay, single transition from in that probability transition matrix. So I to L has to be greater than that, but the minus of this has to be less than. The negative has to be less than. So this we can substitute here. Okay. Okay. So now we have this. Okay. So the maximum over I of this n plus 1 step transition probability, because this is this I can write as an n plus 1 step path from I to j. So if this is less than this entire term, of course I can write the maximum path from I to j. It also has to be less than this, because this is satisfied for all ij. Okay, so therefore we arrive at this expression here. So now we're kind of in good business, because we have the n plus 1 step transition, the maximum path from I to j n plus 1 steps, as a function of n, which is what we wanted, okay, and a function of this alpha. Okay, so we repeat that last statement, last one, okay, and the last one is here, okay, the last line. Okay, so what we can do, okay, so now we have the maximum. So now what we want to do is we want to get the minimum. Okay, so we do exactly the same thing with the same proof. Okay, and with the minimum, what we're going to do is we're going to look at the ij transition. Okay, in n plus 1 steps, and then what we're going to do is we're going to pull out the maximum this time. So we pull out the maximum most probable path in n steps that such that it arrives in state j. Okay, then we play the same game. We bound everything above this time by the minimum, okay, of these of the n-step transition probabilities to get to j. So once we do that, we get this expression very similar to this one up here. Okay, so now we have the maximum path, okay, which is n plus 1 steps to j, and the minimum of n plus 1 steps to j. So this is great. We can take the difference between these two. So if we subtract these equations here, so this first equation minus the second equation, okay, we have this on the right-hand side here, and then these terms over here, okay, on the left-hand side. Okay. So these terms over here on the left-hand side exactly proves the first line of the lemma. Okay. Okay. So the first line of the lemma was here. Okay. So now to prove the second line of the lemma, remember we're going to prove this by induction. But in order to prove this by induction, okay, we need the first initial step. Okay. So the initial step is this. So if if I take the minimum transition probability from L to J, okay, has to be greater than equal to alpha, because we said that alpha was the absolute minimum of all the transition single steps transition probabilities. Then the maximum transition probability has to be greater than or equal to 1 minus alpha. Okay, it's just by definition of what we choose. So therefore, if I take this term, the maximum minus the minimum, is just 1 minus 2 alpha. So that's your first step in the induction process. So we iterate on n. When we iterate on n, one arrives at this, this equation down here. Okay. Okay. So, oops. So this shows us that from here that this limit, okay, is getting, these two limits are, if we take the limit as n goes to infinity of this term, this goes down exponentially in n, okay, and both of these limits are going to converge and they exist and they're going to be greater than 0. Okay, it's going to be greater than 0 because of our initial state that we chose this path with a positive probability. Okay, because, yeah, go ahead.
So it seems to me that the alpha is the minimum smallest number in the transition matrix, right?
Alpha is the smallest number, correct?
Yeah, so that's like kind of the bottleneck of that. So my question is like, the convergence rate is related to the alpha?
Yes, it is. It is. Yeah. In general, it doesn't really matter because it's still going to go down exponentially in n.
Okay.
But it does depend on that alpha. Yes, absolutely. Okay. Any other questions? Yes.
Is the strength of that bound is kind of proportional to the size of the matrix, right?
Excuse me?
The strength of that bound is sort of proportional to the size. I mean, for a very large finite-state Markov chain, the strength of the bound is going to be somewhat weak because alpha is going to be.
Alpha is going to be less. It has to be less than 1/2. Right?
Okay. Yes, but then I mean the strength of the bound though it's not a very tight bound on like max minus min, right? Because in a large.
Yes, this is just a bound, and the bound is when we took that minimum probability path, the L-min. Remember, the bound was actually in here. So we took the minimum probability path in n steps, right? This L-min that minimizes this over I, and then this is where this less than or equal to here is this substitution. Yeah. Okay. Any other questions? Okay. So what we know is that what happens is that these limiting state probabilities exist. Okay. So we have a finite ergodic chain. Okay. And if the probability the elements in this transition matrix are all greater than 0, we know that this limit exists. Okay, but we know that in general that may not be the case. We're going to have some zeros in our transition matrix, right? Okay, so let's go back to these the arbitrary finite state ergodic chain with probability transition matrix P. So in the last lecture, in the last slide, we showed that this transition matrix P of H is positive for H is equal to n minus 1 squared plus 1. Okay, so what we can do is like we can apply lemma 2 to P of H. Okay, with this alpha equals to minimum going from I to j in exactly h steps. Okay, so why is this n minus 1 squared plus 1? Okay, so in the last lecture, so what it means is this. So in here, okay, so what it says is here, this was an example given in the last lecture. Okay, it was a 6-state Markov chain. So what it says is that if n is greater than or equal to n minus 1 squared plus 1, in this case it's going to be 6. So if it's greater than if n is greater than or equal to 26, then I take p to the 26th power. It means it's greater than 0. That means if I take p to the 26th power, that means every single element, okay, in this transition matrix is going to be non-zero. Okay, so which means that you can go from any state to any state, okay, with non-zero probability, as long as n is bigger than that. So basically, in this Markov chain, you go long enough, okay, then I say, okay, I want to go from this, state I to state j in exactly how many steps. There is a positive probability that this is going to happen. Okay, so how did this bound come across? Okay, for instance, in this chain, if we look at P11, all right. Okay. So what do we have here? Okay, so I'm going to look at the transition starting at state 1, and I want to come back to 1. Okay, so you definitely could come back at 6, right? Because these are all positive probability 1. So 6 is possible. So n is equal to 6 is possible. So what's the next one that's possible? N is equal to 11, right? Okay, then the next one is what? 16 is possible, right? So 0 to 5 is impossible, is 0. So if I pick n between like 0 and 5 and 7 and 10, you're toast. You can't get back to 1, okay? And so forth. So 18 is possible, right? Okay. 21, let's see, is 17 possible? Yeah, 17 is also possible, right? So, huh? Okay, so I go around here twice and then the last one. Right? Is that right? Like, so if I go from here to here to here to here, if I go twice and then one more in the final loop. Huh? Oh, it's 12. No, I'm going to go this inner loop right here. So if I go from 1 to 2 to 3 to 4 to 5 to 6, okay, down to 2. Okay, then I go 3, 4, 5, 6, 1. That's 11, isn't it? Okay. So 16 is I'm going to go around the inner loop twice. Okay, go ahead. Question?
So everything 20 and after is possible, right?
No. Is 25 possible? Tell me how you're going to go 25 on this.
You just do 5. You just do the 5 loop.
Yeah, but I want to go from 1 to 1. You're starting at state 1.
Oh, sorry. Okay.
So 1 to 1,
Okay.
right?
Okay, cool. Okay, I see.
Okay, so you know for this one that this bound is actually tight, right? So so 25 is impossible. So P11 of 25 is equal to 0. There's no way you can do that. But for 26 on, then you can. So what you're noticing is that you need this loop of 6 here, and any combination of 5 or 6 is possible. Okay, so basically, in this particular example, if I have if n is equal to, let's see, 6k plus 5j, okay, where k is greater than or equal to 1, because I need a final loop to get back, or j is greater than or equal to 0. So any kind of combination of this one will then I can express n. I can go around it and to give me positive probability going from state 1 to state 1. All right. So I'm going to prove this using an extremal with the extremal property. So we're going to take the absolute worst case, okay? So the absolute worst case is that if you have, for m-state finite Markov chain, is if you have a loop of m and you have a loop of m minus 1. You can't just have a loop of m. The problem is now this becomes periodic, all right? So we can't, so we have to get rid of the periodicity. If you add like a single loop here, that doesn't help you, okay? Then, after 6, then I get 7, 8, 9, 10, 11, 12, that didn't have this. All right? So the absolute worst case for m-state chain is going to be something that looks like this. 1, okay, that goes to 2. You're forced to go to 2, so forth until state m, okay? And then this m is going to go back to 2 or it's going to go back to 1. All right. So in other words, the worst case is if you have to have the n has to be some combination of 6k mk is mk plus m minus 1j. So this will be the worst possible case. Okay, for m-state Markov chain. So it will be mk plus m minus 1. Okay, j. So k has to be greater than or equal to 1. Okay, and then j has to be greater than or equal to 0. Okay, because you need to come back. So I'm just looking at the case probability that started state 1 and I come back in state 1. Okay, so. All right. So how do we get this bound? Well, there is an identity, okay, that says this: if A and B are relatively prime, okay, then the largest n such that it cannot be written. So we want to find the largest n. Okay, such that AK plus BJ, but this is K and J greater than 0. Okay, greater than or equal to 0. okay, that it cannot be written in this form, okay? And the largest one is going to be something of this. The largest integer that it cannot be written is AB minus A minus B, okay? This takes a little bit to prove, but it's not too hard. If you want to know this proof, come see me offline after class. Okay, so if n is, this is the largest integer. If n is equal to this, it cannot be written in this form. But if n is greater than this, then it can. All right. So all we do is substitute m for A and then m minus 1 for B, because m and m minus 1 are relatively prime. Okay. But remember, this k, we have a k here that has to be greater than or equal to 1. We need at least one k. But this identity is for kj greater than or equal to 0. So therefore, we have to subtract out that k. So therefore, we have m times m minus 1, okay, minus m minus m minus 1, okay. But the thing is, we have to subtract out the I'm sorry, we have to add the extra m, because this k is greater than or equal to 1. So we have to add up one of the m's, okay, because of this. All right. So this is just equal to m minus 1 squared. Okay. So this number, if n is equal to this, it's the largest number that it cannot be written like that. So therefore, we have to add 1. So that's why the bound is equal to 1. Okay. So the upper bound that n can be written is going to be m minus 1 squared plus 1. Okay.
You got the one at the end?
Huh? This one? Because this one,
No, this one I got the one at the end.
Oh, I'm sorry.
You already have it in there.
Oh, where is it? No, it's in here, right?
No, it's not here.
Oh, did I? What are you talking about? Where's the one? This
At the end, the last equation.
This one?
Yes.
Oh, okay. This is the cannot largest n.
A minus B.
Largest n which you cannot write. You cannot write this. Okay. So this one is this bound is tight. Okay, it means that this is the one that you can. So if n is greater than or equal to this, then it's possible. This is the largest one, it cannot. Okay, based on this, it cannot. Okay, so we have to add the 1 because, so therefore, in here, this is equal to 26. So starting from 26, 27, 28, you can do that. Okay. Okay, any questions? Shane? Huh? That means the greatest common divisor is equal to 1. Yeah. Okay, so if we take h here, okay, so h is going to be positive. So if h is equal to m minus 1 squared plus 1, okay, then now all the elements are positive, right? Because we just proved that we can write this, okay, we can visit, every state can be visited by any other state with positive probability. Okay, so instead of looking at p, we know that this p of h is positive for h is equal to this bound. Okay, actually it's positive for h greater than or equal to this bound. So what we do is we apply this lemma 2 to probability to this transition matrix P of H, okay, where we have pick alpha. Remember, alpha is the single step transition probability. So instead of the single transition, we have lumped this P into P to the H power. Okay, so it's like H steps because we proved the result before for positive P, right? So this P to the H is positive, so we can take alpha is equal to minimum from I to j of P to the H in this matrix. Okay, so it doesn't really matter what the value of alpha is, only that it's going to be positive. And it has to be positive because it's a probability. Okay, so what happens is like if we follow the proof of the what we just showed in the lemma, then we show that the maximum path from L to J, okay, and h times m. Okay, so m is going to be an integer. So in multiples of h, right? This upper limit, okay, is going to be equal to the lower limit. So the most probable path, okay, is equal to the least probable path. Okay, okay. So this is a multiple of h's. So if we take as m goes in infinity, this has got to equal to okay, oops, this is going to be, should be equal to pi sub j, excuse me. Okay, there's a little typo here. Okay, so it's, and this is going to be greater than 0. So the problem is like now we've shown it for multiples of h's. What about the h's in between? Okay, but the fact is that we show in lemma 1 we show that the maximum path from L to J in n is non-increasing in n. So all those states, all those paths, okay, the transition probability for the paths in between these multiples of h's, okay, in between them, okay, is going to be non-increasing in n. So even if we're taking like these multiples of h of n, here, 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 and we know that this limit is increasing, we know that all the ones in between them are also going to be increasing to the same limit because of lemma 1. To remember, it's the maximum is going to be non-increasing, and the minimum is going to be non-decreasing, minimum path. So it must have the same. So this must have the same limit as the as this multiple of this. So the same limit applies. Okay. So any questions on this? So this is how we prove it for the arbitrary finite state ergodic chain when we have some zero probability transition elements in the matrix P. Okay. So the proof is the same. All right. Oops. Okay. So now for ergodic unit chain, so we see that that this limit as it approaches infinity from I to j of n is going to just end up in the steady state transition pi of j for all I. So it doesn't matter what your initial state is. As n goes to infinity of this path, as this Markov chain goes on, you will end up in state j with probability pi sub j, okay, where pi is this probability vector. So now we have the steady state vector, and then we can solve for the steady state vector solution. So this pi p is equal to pi. Yeah, go ahead.
Where did you prove that the sum of all the pi j is equal to 1? Because you say that we prove that this is probability vector, but we prove only that it is non-negative.
It's non-negative. But the thing is, like, because as n goes to infinity, you have to land up somewhere, right? It's a finite state Markov chain. You have to be somewhere. And the fact that you have to be somewhere, your whole state space has to add up to 1. Okay? Because it's a constant. Remember, for every j, as n goes to infinity, it goes to pi sub j. So you have that for every single state. And then you have to end up somewhere. So you have to end up somewhere. The space has to add up to 1. Yeah, good question. Okay, so why are we interested in this pi sub j? The question is that because in this recurrent class, it tells us that as this goes to infinity, we see this sequence of states going back and forth, and we know that as n goes to infinity, we have some probability, pi sub j of landing in state j, pi sub I landing in state I, and so forth. So it says that as in the n step, as n goes to infinity, that this is the fraction of time that that state is going to be visited, right? Because in each step, you have to make a transition. Okay, so it's kind of the expected number of times, okay, per unit time. So it's divided by n is going to be that fraction of time that you're going to visit that state. It's a fraction of time that you're going to be in that state. Okay, is this limiting state as n gets very, very large. Okay, so we will see that when in the next few chapters, when we do a renewal theory, that this will come into a useful play, and we give a different, slightly different viewpoint of it. Okay, so it's very easy to extend this result to more general class of ergodic unit chains. So remember, the ergodic unit chains, now we have to increase these transient states. Okay, so before we proved this, we just proved it for, it contains exactly one class. It's aperiodic, so we have no cycles, no periodicity in this Markov chain. And so we know that these the steady state transition probabilities have a limit, and the upper limit and the lower limit of these paths as they go to infinity, the fact that you end up in a particular state has a limit. And we have this steady state transition probability vector that describes this. So now we have these transient states. So these transient states, this Markov chain, what happens is there exists a path, okay, that this transient state is going to go to a recurrent state. So once it leaves this transient state, it goes to recurrent state, it's never going to come back. So there is some probability alpha, okay, that it's going to be in there's of leaving the class at each step. Okay, so there's some transition probability in this transient state that's going to be out. Okay, and the probability of remaining in this transient state is just 1 minus alpha to the n. And this goes down exponentially. So what this says is that eventually, that as n gets very large, it's very, very hard to stay in that transient state. So it's going to go out of this transient state, and then it will go into the recurrent class. So when does this analysis for this, what happens in the probability, this steady state vector is those transient states, this pi will be equal to 0. Okay, so this distribution is only for, that's going to be non-zero for recurrent states in this Markov chain. And the transient states will have probability equal to 0. Okay, here. In the notes, they just extend the argument, but you need a little bit more care to show this. And it divides the transient states into a block, and then the recurrent classes into another block. And then shows that, that these transient states, limiting probabilities is going to go to 0. Okay, let's see. Okay, so this says just what I said, that these transient state decays to 0 exponentially, and one of the paths will be taken eventually out of it. So for ergodic unit chains, the ergodic class is eventually entered, and steady state in that class is reached. So every state j, we have exactly this: the maximum path, okay, from I to j in n steps, okay, and the minimum path. We look at the minimum path in n steps and the maximum path in n steps, okay. And for each n, we take the limit as n goes to infinity. These guys, these limits are exactly equal, and it equals to this pi of j, where it's equal to the jth state. So your initial probability, initial states, how you went, the path that you have gone is completely wiped out, and all that matters is this final state, okay, as n gets very large. So the difference here is that pi j equals 0 for each transient state, and it's greater than 0 for the recurrent state. Okay, now, so other finite Markov chains. So we can consider a Markov chain with several ergodic classes, because we just considered it with one ergodic class, right? So if the classes don't communicate, then you just consider it separately. So you figure out the steady state of transition probabilities for each of the classes separately. But if you have to insist on analyzing the entire chain P, then this P will have m independent steady state vectors. Okay, okay, and one okay, and one non-zero on each in each class. So this piece of n is still going to converge, but the rows are not going to be the same. So basically, you're going to have blocks. So if you have one class, say 1 through k is going to be in one class, and then k through L is going to be another class, and then L through Z is going to be another class. You'll have a block. So this steady state vector is going to be in blocks. So in the okay, so you can see the recurrent classes only communicate within themselves. So because these don't communicate, right? So they're separate. So that you're going to have a lot of zeros in the limiting state. In this, if you look at this piece of n goes to infinity. Okay, so there are m set of rows, one for each class, and a row for each class k will be non-zero for the elements of that class. Okay, so then finally, if we have periodicity. So now if we have a periodic recurrent chain with period d. Okay, so we had the 2 where it's just period 2. So with periodicity, what you do is you're going to divide these classes into d different states. So you have to go to one state. So if there's d states, if this is a period of d, you divide it into, you separate or you partition the states into d of them, d subclasses, with a cyclic rotation between them. So basically, each time unit, you have to go from one class to the next class. Okay, and then when you do that, then for each class, you could have the limiting state probability. Okay, so in other words, you are looking at this transition matrix, pi d. Because when it's cyclic, it totally depends on which one you start out at. So it has, but if you look at the d intervals, okay, then that becomes an ergodic class by itself. And there are exactly d of them. Okay, so limit as n approaches infinity of p of nd, this thing also exists, but exists, okay, in the subclass sense of there's d subclasses if it has a period of d. So that means the steady state is reached with a subclass, but the chain rotates from one subclass to another. Okay? Yeah, go ahead.
In this case, for example, the simple chain with 1 and 2, with
Yeah.
1 and 1,
Yeah.
it doesn't converge. So, and
No,
here
it
you
does.
say
It gets 1. It
Sorry?
converges to 1. Okay? So it's 1, and then it's going to be 1.
It's 1, 1, 1, 1, 1, 1.
Yeah.
So it's called, you call here like it's reached.
No. It converges for here. But this d is equal to 2 in that case. Right? Yeah. So you have to do nd. So you look at p squared. So if I look at p squared, I'm always in 1. 1, 1, 1, 1, 1, 1, 1, 1, 1. That's converging. The other one is 2, 2, 2, 2, 2, 2, 2. That's also converging. Right. Yeah. Okay. So is there any other questions about this? Okay. That's it. Thank you.